Thank you very much for Martin, and thank you inviting me to interesting workshops. So I'm Keiko Kuge from Kyoto University. So as you know, the physical mechanism of deep earthquake is not fully understood. So one of the properties to be explained by candidate mechanism is termination of deep earthquakes at depths around 700 kilometers, as shown in, No, it doesn't work. Yes, yeah. As shown here. So near these depths, there exists a 660 discontinuity in the mantle. So the relationship between the seismicity and 660 discontinuity is very important to consider the mechanism of deep earthquake. An exceptionally deep and large earthquake occurred 2015 west of Ogasawara Island. So the depth determined by USGS and JMA was larger than the 660 kilometers. So hypocenter is located here and isolated from Wadachi-Benioff zone in this region. In this region, Pacific plate subduct to the west, and then to the north, the plate is stagnant. To the south, the Pacific plate almost vertically subduct. So this region is transient from slab stagnant to vertical descent. So velocity structure was examined in this region. So this is a result from Obayashi et al. By P-wave tomography. So this is a cross-section image including Ogasawara earthquake. So this blue area indicates subducting Pacific plate. So Obayashi et al. Suggested Ogasawara earthquake occurred in the heel part of stagnant slab, which descend to initiate slab penetration into the lower mantle. Zhao et al. Provided slightly different images by P-wave tomography. So here, images of cross-section in this region. Zhao et al. Provided this schematical illustration of slab from their result. So they suggest Pacific plate is split. So here, north of Ogasawara earthquake. So slab configuration in this region seems controversial. P and S waves from the Ogasawara earthquake were recorded by many seismometers in the world and also in Japan. This panel indicates the station of broadband seismic network in Japan, FNET. So after the main shock, largest aftershock occurred with magnitude 4.9. So this is a good site to see structure. So data from eastern Japan are likely to affected by subducting a Pacific slab in the northern part. So I am interested in data recorded by Western Japan to see structure around this region. So in this talk, based on observed regional P and S waves, I consider structure surrounding the Ogasawara earthquake by addressing 660 discontinuity and slab configuration and anisotropy. So I start from 660 discontinuity. So these slides show effect of 660 discontinuity on theoretical P waveforms. In the left, I assume discontinuity above the source. In the right, I assume discontinuity below source. In both figures, vertical axes indicate distances from 0 to 20 degrees. In the left, for discontinuity above the source, you can see a simple pulse over the range. On the other hand, you can see several pulses for discontinuity below the source. So this is caused by triplicated waves by the discontinuity below the source. So the Western Japan is located here. So we distinguish these two features from the observation. So in the left-hand side, I show observed displacement waveform of P waves. in a distance range from 7 to 19 degrees. So you can see a simple single pulse in observation. In left-hand side, I show theoretical waveform for 5 different depths of 660 discontinuity in ESP91. So deep to the right, shallow to the left. The center is hypocenter depth. So for deep discontinuity, you can see a complexity in waveforms due to triplication. So 2 pulses, precursor, and trapezoid shape. For shallow discontinuity, you can see a simple pulses, so which is similar to the observation. So the observation lack triplicated waves. 660 discontinuity above the aftershocks fit the observation. So how shallow discontinuity can be accepted by observation? So next, I use short period P waves located closer to the aftershock. So here, I show velocity seismograms recorded by HiNet in Japan at distances from 7 to 8 degrees. So you can see P waves, and the coda continues about 4 seconds. In the right-hand side, I show a theoretical waveforms for 2 different depths of discontinuity. Both discontinuity are located above hypocenter. So you can see here and here SP conversion phases due to discontinuity. The time delay depends on depth. So for this case, these arrival are too late compared to the duration of observed coda. However, these phases arrive well within the observed coda. So using here and here, I also calculated the vespergrams here. So these comparisons also suggest 660 discontinuity is likely about 20 kilometers above the aftershock. The data from the main shock also suggest shallow discontinuity. So this slide shows variation of finite fault model waveform fit with changing 660 discontinuity. Horizontal axis indicate assumed discontinuity depth, and then vertical indicate the variance reduction, which show waveform fit. So larger value means waveform fit better. And then this green line indicates the hypocenter depth. So you can see a large value in the left-hand side of this gray line. So when 660 discontinuity is assumed above the hypocenter, main shock waveform fit is better. So a significant subhorizontal 660 discontinuity could not be located below the aftershock and also main shock. The observed waveforms are sensitive to the relative location between the aftershock and discontinuity, not the exact depth of discontinuity. The discontinuity may be around 20 kilometers above the aftershock. The master event analysis relocated the aftershock to be 6 kilometers deeper compared to the main shock. So the depths of 660 kilometer discontinuity are 650 kilometers when we use USGS main shock hypocenter, and 670 kilometers for the JMA main shock hypocenter. At the end of this topic, I mentioned a local small jump might just below the aftershock too. So this is again velocity seismograms recorded by HiNet. And then these portions are zoomed up here. And then you can see a small negative precursor here. So theoretical waveforms for 660 discontinuity just below the aftershock with reducing jump produce negative polarity. Although these theoretical waveforms cannot fully explain the observation. Global data from the main shock do not favor this model. So if there is a structure around here, this structure should be local. So I summarize my result here on a tomographic image by Obayashi et al. So 660, significant 660 discontinuity can be located above Ogasawara earthquake. There might be a small local velocity jump just below Ogasawara earthquake. So now I move to slab configuration in this area. Furumura and Kennett and Furumura et al. Indicated Pacific slab causes a difference in P and S arrival times between high and low frequency. So this is their example. These traces are recorded by Tomari here for this deep earthquake. You can see long period energy arrive early compared to the high frequency energy. So they suggested laminar structure within the slab produces delayed arrival of high frequency P and S wave. They also suggest that slab structure such as metastable olivine wedge enhances the delays. So these different arrivals between the low and high frequency indicate seismic waves can travel within the slab. So I examined this feature in Ogasawara region. So there is a broadband station here, OSW. And the aftershock is located here, and then a deep earthquake located here. This earthquake occurred within the Wadachi-Benioff zone. So data from these two earthquakes are shown in right-hand side. The top are original data, and then second traces indicate low-pass filtered envelope. The third traces indicate high-pass filtered envelope. For deep earthquake in Wadachi-Benioff zone, we can see a time difference between here and here in peaks. So these observations suggest these P waves can travel within a slab. On the other hand, for aftershocks, we cannot see such a time difference. So the aftershock P waves are unlikely to propagate within slab. So this is consistent with the idea of slab dipping to the east, deeper than around 500 kilometers. So similar difference observed in Western Japan. So now we measure the time difference between the high and the low frequency, and then show the value by using different color scale. So warm color indicate late high frequency. Cold color indicate early high frequency. In Western Japan, you can see black triangle. These correspond to no time delay. So I show the observation for deep earthquake in Wadachi-Benioff zone. So you can see a warm color in Western Japan. So the P waves are likely to be affected by slab. This earthquake was located within the depths of stagnant slab. So observation from aftershock is rather similar to the observation for shallow events, so stagnant slab is there. So this case is observation for depth 400 kilometers. So this earthquake is located just above stagnant slab. So you can see no time delay in Western Japan. So these comparisons suggest aftershock P waves traveled for Western Japan little within the slab. So finally, I talked about anisotropy. So here are shear waves observed in Western Japan from the aftershock. So SH waves and SV waves. these waveforms are aligned by peaks of SH waves. So red line indicates the time when peak of SH wave arrived. So distances ranges from 7 to 11 degrees. And then you can see a simple single pulse in SH wave. And then in SV wave, you can see energy appear in the right-hand side of this red line. So that means SH peaks arrive earlier than SV peaks. So I test this observation by 660 discontinuity, effect of 660 discontinuity. So now I show here the observation, which is the same as previous slide. So SH, a simple single pulse here, and then SV peak arrive later compared to the SH wave. In right-hand side, I show theoretical waveforms for 3 different depths of discontinuity. Red line indicates the time when peak of SH wave arrived. For deep discontinuity, you can see early SV arrival. And then you can see precursor in SH wave. For discontinuity just below the aftershocks, we can see some complexity in our waveforms. So discontinuity about the aftershock explains the observation better. So this is the same as the case for P wave. On the other hand, all of these 3 cases cannot explain SH peaks arrive earlier than SV peaks. So I measure the time difference between the peak, SH, and SP, and then plot them on the map. So now this is the time difference between the SH and SP, and the warm color indicates fast SH arrival. Cold color indicates late SH arrival. In Western Japan, we can see a warm color here, so SH wave arrival, fast SH arrival. So a shear wave from the Fiji island travel from the southeast. So similar to the aftershock, similar one from the aftershock. So I test the time difference in the same way and then show the result. So this is the case for 2 earthquakes. So you can see a warm color in Western Japan here, but for this earthquake, we cannot see cold color appear in Western Japan. So fast SH wave arrival are not always seen for teleseismic earthquake in Fiji Island. The fact suggests the cause of fast SH wave arrival is likely offshore toward the aftershock. One possible explanation for time difference between SH and SV is anisotropy. So this slide shows the relationship between anisotropy and shear wave splitting. The incident shear wave is simple. By traveling anisotropic layer, we can see 2 separated phases. Oscillation along fast direction arrive earlier compared to the oscillation along slow direction. So this shear wave splitting can be characterized by 2 parameters: fast direction and time delay between 2 pulses. By using the correlation technique, we estimated these 2 parameters from broadband data in Japan. So this is the result. So this green bar indicates the fast direction. The length of green bar indicates amount of time delay. Amount of time delay are also shown by different color scale. In Western Japan, you can see green bars aligned almost east-west. I compare this result with the result for different earthquakes in Wadachi-Benioff zone. So this is a result, and then results are limited at station where incident angle is smaller than critical angle. It should be noted for all stations for this case, incident angle is predicted to be smaller than critical angle because the depth is very, very large. So you can see the first direction aligned northeast, southwest. So we can see difference between here and here. So two earthquakes are distinctly very different in depth. So lay paths are very different in deep portion. Although it is very difficult to locate the area, anisotropic area, but difference may be attributed to deep portion along lay paths. So I summarize my result in this slide on image by Obayashi et al. On illustration by Tsao et al. Based on lack of triplication, 660 discontinuity, significant one, can be located above Ogasawara earthquake. There might be a small local velocity jump just below the earthquake. We observed lack of P arrival time difference between low and high frequency. Such an observation in Ogasawara region suggests slab bend to east deeper than 500 kilometers. Such observation in Western Japan suggests the presence of slab is not required in the northwestern side of this earthquake. We observed early SH arrival in Western Japan corresponding first direction almost east-west, which imply the presence of anisotropic area. It might be a manifestation of horizontal flow in a deep mantle. So I indicated shallow discontinuity here. So at the end of this talk, I discussed what could cause earthquake rupture below 660 discontinuity. So melt and shear instability are possible once rupture is triggered. A popular candidate for deep earthquake is transformation faulting in metastable olivine. And then Green and Thor suggested termination of earthquake at 660 discontinuity can be explained by these two features. This is a figure from Green and Thor. And then this line indicates the post-spinel transition of olivine. And then this transition becomes deep due to the low temperature. So this topography can change in space. Then the topography changes rapidly. It is hard to detect by seismic wave. So idea is significant 660 continuity can be predicted around here, and then maybe a small local velocity jump corresponding to here. However, a question remains for this idea. So can metastable olivine survive at such a depth? So I propose another idea. So in this figure, dashed line indicate the transition of metastable anesthetate to eliminate. So I focus on this point. So anesthetate can appear as a metastable state in a deep portion and olivine. And also the transition of eliminate to perovskite could occur deeper compared with the olivine system. So very, very schematical image is like this. And then post-spinel transition of olivine appear, and then can control velocity jump. If metastable instability can trigger deep earthquakes, and 660 velocity discontinuity is characterized by major olivine, earthquake rupture may occur below 660 velocity discontinuity, like this. So for this case, probably a significant 660 discontinuity looked here, appear here, and then maybe small local velocity jump correspond to here. So this last slide summarizes my talk. The structure surrounding Ogasawara deep earthquake was explored by observed regional P and S waves. The 660 discontinuity can be located about the earthquake. A local small velocity jump might also exist just below the earthquake. Different discontinuity are not required for P and S wave. If a slab extends to the earthquake, it can bend to east just above the earthquake. In the northwestern side of earthquake, the presence of slab is not required, and anisotropy with first direction nearly east-west can exist. These results appear to agree with the slab image by Cao et al. Thank you very much for your attention.